We're going to be taking tomorrow, May the 4th, off because of May the 4th, as is tradition. So today's show will have This Week in Rocket History. As Beth said in this week's newsletter, you don't have to be a Star Wars fan. You don't have to even see any of the movies. But we take this day to celebrate one of those moments in geekdom that is just joyous and fun. And so we will not be recording the Daily Space that day. As Will Wheaton once said, don't let anyone tell you that that thing you love is a thing you can't love. Don't anyone ever tell you that you can't love that. You find the things that you love and you love them the most that you can. End quote. Instead of a show, tomorrow we're going to release a promo for this year's big events. And thanks to a combo of weird house construction and cool ideas, we have something new to introduce. Anyways, hello and welcome to Explodey Star Day and Launchy Rocket Day.
We've got a lot of rockets, 4 different rockets in fact, and a helicopter even caught part of one of them.
And there is more science than just the explodey star, although I'm super partial to the explodey star. We also have moons, Mars, and magnetic fields.
The middle of this episode is brought to you by the letter M.
All that and more, right here on the Daily Space. I'm your host, Dr. Pamela Gay.
And I'm your host, Eric Mattis.
And we are here to put science in your brain. Lately, I've been seeing a new rash of photos showing how folks have aged as the hashtag first headshot gains steam. These images give a chance to see just how brightly folks shone when they were young. They help train machine learning algorithms to better identify people. You knew you were donating training data, didn't you? And these images give us a chance to better understand how aging in different environments can really have an impact. In the latest issue of the Astrophysical Journal, the supernova remnant 2014C gets in on the game, and in a new paper led by Benjamin Thomas, researchers show us how this one grand system has changed over the years. Back in 2014, a bright splot was spotted near the central region of the galaxy, NGC 7331. Over the first 500 days after the initial explosion, the system was watched in every wavelength of light. This wasn't just a massive star going boom one day. This was a massive star in a binary system that had its outer layers of hydrogen torn away by its companion, until one day its core was out of fuel and its outer layers were a glimmer of their past glory. On that day, the star exploded. The explosion was initially classified as a type 1a supernova, the type of supernova that occurs when a white dwarf star sucks too much material off a companion and gets so massive it is unstable. This misidentification had the whole who stole mass from whom completely backwards, and it was only 127 days after the explosion that the chemistry of the blast revealed its weird, true origin. Astronomers are bomb investigators. We just work with really big thermonuclear bombs. Over time, things got only weirder. The system emitted more X rays, while the optical light stayed constant. Over time and with more telescopes, it was found that X ray light and the cooler light of infrared and radio emission all increased and then decreased over time. This bizarre phenomena isn't natural to a supernova, but can be created as its light and energy blast surrounding material and echoes in interesting ways. In this paper, the research team proposed that the star system had shed material earlier in its evolution and left behind a ring, like my shedding dog might leave behind a ring of fur. As the explosion expanded, the shock wave hit this material, and the energy produced the glow we see in optical light, while the radio emission came from parts of the shock wave that avoided the inner ring of material and interacted with material farther out. What's particularly cool is they were able to map out the velocities of the gases around the system at different temperatures, mapping out loosely where the slowdowns and clear traffic can be found. The paper is a really good read, and if you are a chemistry junkie that can dig into Doppler shifted gases, go give it a read. We have it linked on our website, dailyspace.org. For the rest of you, it's enough to know that if you want to escape a supernova quickly, it is best to steer as far away from a surrounding ring of material as possible. And there's going to be a whole lot of folks watching that heated pileup at the ring, even 7 years later.
There have been a number of rocket launches since our last show, including 3 on April 29th, and Starlink and Chinese launches on the weekend of the 30th. Starlink launches are fairly routine, but there was a milestone of sorts set with this one. SpaceX broke their own record for Falcon 9 booster turnaround time, 21 days after its previous flight on the AX-1 crewed mission on April 8th. We haven't talked a lot about Russian launches lately, but it is worth noting that over the weekend of April 30th, Russia conducted the first orbital launch of an Angara 1.2 rocket. It has been in development since 1992. Unlike the Angara A5, the Angara 1.2 has no boosters. It launched a military payload that has been designated Cosmos 2555, the details of which were, of course, not disclosed. Another unique launch that took place over the weekend was the third launch of a Long March 11 from an ocean barge. On April 30th, it delivered 5 spacecraft in the Jilin 1 series of high-resolution optical satellites to orbit. Overall, the Long March 11 has launched 13 times, including 3 ocean launches.
Finally, Rocket Lab launched another Electron rocket, this one called There and Back Again. The name was not only a reference to Lord of the Rings, which was filmed in New Zealand where the rocket launched from, but also that this mission would be the first attempt at a mid-air recovery of the rocket's first stage. The whole CosmoQuest team was excited about this launch, so we hosted a launch party right here on Twitch. Let's watch the launch. Rocket Lab had previously tested the reentry and mid-air catch separately. This was the first attempt to do both during an operational mission. 3 previous missions made it through reentry to the water intact, and the boosters were recovered by one of their ships. An hour before the launch of There and Back Again, the helicopter took off. About 150 seconds after launch, the stages separated and the first stage re-entered the atmosphere. At 13 kilometers altitude, a drogue chute stabilized the stage for the main chute deployment at 7 kilometers altitude. Unfortunately, the catch was not completely successful. The helicopter was able to catch the first stage, but the pilot saw something he didn't like with how it acted and released the load before it could be placed on the recovery ship. It splashed down in the ocean and was recovered by the ship, so it wasn't a complete failure. Better luck next time, Rocket Lab. There and Back Again was the 26th launch of an Electron rocket. and it successfully delivered 34 satellites into orbit for a variety of customers, including Asterix, a New Zealand-based company that makes solar panels for small satellites, and spaceflight, which organizes ride shares for many customers. You may recall that there is a citizen science program involved with NASA's Juno spacecraft and run by Planetary Science Institute senior scientist Kennedy Hansen. For this program, everyone is invited to download the raw images taken with the JunoCam imager on board the spacecraft and process them to their heart's delight. We've seen true color renders, highly stylized variations, and everything in between. Now, with Juno making flybys of some of Jupiter's moons, we're even getting to see shadows on the surface of Jupiter. In an image processed from Juno's 40th flyby, citizen scientist Thomas Thanopoulos created an enhanced color image of the gas giant with the shadow of Ganymede seen on the cloud tops. If you were there, you'd be seeing a solar eclipse. You can see the full image in our show notes at dailyspace.org, where we will also have a link to the image processing website. Go forth and make science art. Another moon getting a lot of press these days is Saturn's moon Titan. Scientists are constantly comparing Titan to Earth, what with the liquid features, atmosphere, and weather. But not everything is similar. Those liquid features are made of methane. The atmosphere is far thicker than Earth's, and the local winds build dunes made of hydrocarbon sand. Now, new research published in Geophysical Research Letters and led by Mathieu Lepartre models just how grains of sediment could form and exist on the large moon. On Earth, our sediment consists primarily of silicate rocks and minerals which erode down into grains over very long periods of time. Silica is pretty hardy after all and doesn't break down easily, so it takes erosion by wind and water to produce sand. However, hydrocarbons are organic compounds, and they are more fragile than silicate grains, which means they should become dust over time. Lepartre explains, quote, as winds transport grains, the grains collide with each other and with the surface. These collisions tend to decrease grain size through time. What we were missing was the growth mechanism that could counterbalance that and enable sand grains to maintain a stable size through time, end quote. To reconcile this mystery, the team turned to ooids on Earth, which are found in shallow tropical seas. Ooids are small spherical grains made when calcium carbonate is removed from the water column and attaches to a silica grain like quartz. The carbonate builds up in layers, growing in size, but that size is then kept in check by the erosion caused by waves and storms. This process leads to grains that stay consistent in size. And that process could solve the mystery of Titan sand dunes lasting despite the more fragile grains. Lepartre explains, quote, we were able to resolve the paradox of why there could have been sand dunes on Titan for so long, even though the materials are very weak. We hypothesized that sintering, which involves neighboring grains fusing together into one piece, could counterbalance abrasion when winds transport the grains, end quote. Further comparisons to existing data about Titan's climate and sediment transport mechanisms match what could be happening to where it is happening on the moon. There are dunes at the equator, plains in the mid-latitudes, and labyrinthine terrain near the poles. Titan's seasons drive the sedimentary cycle, just as happens on Earth and has happened long ago on Mars. As Lepartre notes, quote, it's pretty fascinating to think about how there's this alternative world so far out there where things are so different, yet so similar, end quote. Speaking of Mars, a press release was issued from the Planetary Science Institute that looks at an intriguing darker layer of rocks on Mars at Mount Sharp, near where Curiosity is roving. This layer is darker, stronger, flatter than the surrounding sulfate bearing rocks and has been observed using orbital data from the HiRISE camera aboard the Mars Reconnaissance Orbiter. The layer is also weathering differently than the layers above and below, suggesting it's made of a more erosion resistant rock. Because of the standout nature of this rock layer, geologists refer to it as a marker horizon. We use marker horizons on Earth to constrain time stratigraphic features where we know that the layer formed during one single event or a specific period of time. That layer then marks the rocks below as deposited before the event and therefore younger, and the rocks above as deposited after the event and therefore older. Think the KT boundary and the iridium that marks below here are dinosaurs. Above here, not so much. On Mars, that means something interesting happened to cause a break in the sedimentary deposits. Lead author Catherine Whites explains, quote, some event occurred within Gale Crater during the deposition of sulfate-bearing sediments that resulted in a different kind of rock unit. The marker horizon is distinct in appearance from the sulfate-bearing rocks above and below, indicating an environmental change occurred for a brief time, such as a drier period, or perhaps a regional event like an explosive eruption from a nearby volcano that deposited ash across a large area which included Gale Crater. End quote. It could even be the same rocks as above and below, but the marker horizon became harder and more resistant to erosion for some reason. As Whites notes, quote, all of these potential origins require the presence of at least some water to cause cementation that hardened the horizon. Our orbital observations currently favor a hardened sulfate or volcanic ash origin, but we will have to wait until the Curiosity rover reaches the horizon in the coming months before determining which origin is most plausible. End quote. And that gives us something to look forward to. We'll bring future results of Curiosity's exploration to you right here on the Daily Space. This work was published in the Journal of Geophysical Research, Planets. Before jumping to this week in rocket history, I just wanted to take a quick look at some new results about our sun. In a new paper in Nature Communications Physics, researchers led by Yi-Hsu Lin look at how the roiling coils of plasma in the outer layers of the sun can reconnect and release energy. Working from first principles, like when a math or science teacher asks you to prove a theory from base equations, they worked out how energy flows out of a system when the north and south parts of a magnetic field come together. The basic physics behind what they studied is used in all kinds of different sensors, including the ones that tell your iPad or AirPod Max headphones to turn off when they're in their case. The details, however, are a lot harder to work out when the magnets involved are the ions and electrons moving in the sun's plasma. But solving hard things is why a lot of folks go into physics. And this team has a solid model that makes solid predictions. And conveniently, our sun is moving into a much more active period and should be providing all the flares this team needs to confirm and refine their work. So next time you flip closed a flip phone, know you are relying on the same physics seen in the sun. Now, let's welcome back Eric as we talk about this week in rocket history. Stay tuned.
We've been hyping up this installment of This Week in Rocket History all episode. So what is it? Another foreign satellite launched on a US Scout rocket, the UK's Ariel 3. Ariel was a British satellite program that made the United Kingdom the third country to operate a satellite. Ariel 1 was launched in 1962, 2 in 1964, and 3 in 1967. Ariel 1 and 2 had British-built experiments on an American satellite bus. Development of Ariel 3 started in 1962 with the formal proposal of the instruments to NASA from British scientists. A year later, in 1963, all of the instruments were agreed upon by the two teams, but for a variety of reasons, the satellite construction did not start until 1964. Ariel 3 was the first satellite built in the UK, and the British team was responsible for building a prototype, engineering models, and 2 flight satellites. The satellite's orbit was changed from an originally planned 50-degree inclination to 80 degrees to give the molecular oxygen experiment access to other latitudes to collect data, important because the solar cycle was picking up at the time. Ariel 3 had 4 solar panels and 5 experiments and weighed just under 90 kilograms. The main purpose of the satellite was to observe variable stars and galactic radio sources. Unlike the San Marcos satellites we talked about last week, Ariel 3 was launched from a Scout A rocket from Vandenberg Air Force Base on May 5, 1967. It was originally planned to be launched from Wallops like San Marco 1, but was moved to Vandenberg because of the new orbit. The satellite body had 3 paddles, which Gordon on our editorial team thought looked more like snowshoes, where solar panels and some of the instruments were mounted. The terrestrial radio noise experiment was designed to quantify the radio noise at the satellite altitude by allowing scientists to more easily tell what was a terrestrial radio source and what was a galactic radio source. The experiment demonstrated that most of the noise came from frequencies just above the quote ionospheric critical frequency, where terrestrial transmissions at lower frequencies are blocked and reflected back towards Earth. Additionally, the noise from higher frequencies was so spread out that it was easy to filter. It also measured the density and temperature of electrons with the Langmuir probe and radio frequency capacitance counter. The Langmuir probe measured the temperature of electrons by comparing the voltages of 2 different spheres on the spacecraft. The voltages were constantly changed in reaction to electron temperature to maintain a fixed ratio between the 2 spheres. The electron temperature was determined by comparing how the voltages actually changed compared to the fixed ratio. The radio frequency capacitance probe measured electron density by counting the change in current between 2 grids. Like the Langmuir probe, it operated by switching voltages rapidly. To properly measure the change in current, it needed to be at space potential, or the same arrangement of positively or negatively charged environment of space for at least part of the sweep. This was enabled by changing voltages. The 2 experiments actually used the same probes, with the experiments switching every 5.2 seconds. The last major experiment on Ariel 3 counted molecular oxygen, a hazard in low Earth orbit, which can damage spacecraft. It does this by chemically interacting with almost everything, breaking down materials exposed to UV radiation. Indeed, the experiment was damaged by this, and after 20 days, the sensor was ruined. Fortunately, ground experiments indicated that this would happen, so nothing was lost. All of the other experiments continued functioning through the end of the mission, exceeding their 1-year design lifetime. Ariel 3 operated normally until its tape recorder failed in early 1968. In late 1968, its battery failed, meaning it could only be used when the satellite was directly lit by the sun. In early 1969, it could only downlink to 1 ground station, and it was finally turned off by mid-1969. Ariel 3 re-entered the Earth's atmosphere in 1970, when its orbit decayed. And now for some statistics. The number of toilets in space is 8, 4 on the ISS, 1 on Soyuz MS-21, 1 on Crew Dragon Endurance, 1 on Crew Dragon Freedom, and 1 on Tianhe. We keep track of orbital launches by launch site, also called spaceport. Here's that breakdown. USA 24, China 12, Russia 4, Kazakhstan 3, New Zealand 3, India 1, Iran 1. From those 48 launches, a total of 792 spacecraft were put into orbit. The random space fact for this week is that a stand of trees at Birr Castle in Ireland is in the shape of a spiral galaxy, to commemorate the 150th anniversary of the discovery of the spiral structure of the Whirlpool Galaxy, Messier 51, by the 3rd Earl of Ross. The lime trees were planted to match the shape of a sketch he had made. He used the 1.8-meter reflecting telescope, the Leviathan of Parsonstown, to make the discovery in 1845. This has been the Daily Space.
You can find more information on all our stories, including images, at dailyspace.org. As always, we're here thanks to the donations of people like you. If you like our content, please consider joining our Patreon at patreon.com/CosmoQuestX.